Let me go to. Oh, somebody said something. Let me see here in the chat. Oh, okay. I just saw your message, Osorio, Miss Osorio. Make sure I record your attendance.
Bless you.
Thanks. Okay, so as I was saying, let me bring up. Oh, so let me bring up assignment number 5. Okay, so um, I'm sure we did all of the. Oh, hold on. Did we do number 12? No. Okay, so I misspoke. Um, because number 12 has to do with gas stoichiometry. So that's very important. Let's talk about this. All right. All right. So this question, they gave you a balance equation. Oh, well, by the way, have any of you tried this question? Have any of you attempted? If not, oh, let me get my.
But I think I didn't attempt it, but I think I know how to go about doing it.
All right. Well, let's see. Let me get my pen. Okay. So, turn on. Okay. So the question says it gives you the balance equation, right? And then it says in the A part, how many liters of ammonia at 850 degrees and 5.00 atmospheres are required to react with 1.00 moles of oxygen in this reaction. So they gave you the volume of ammonia, they gave you its temperature, and they gave you its pressure, but they're asking for and they gave you the moles of, I'm sorry, I misspoke. They're asking for the volumes, how many liters of ammonia. They gave you the temperature, they gave you the pressure, and they gave you the moles of oxygen involved in the reaction. So what do you think your first step would be in order to solve this problem?
We're trying to get the volume. So I think the first thing to do would be to find out how many moles of ammonia are needed to react with 1 mole of O2.
Okay, very good. How would you go about doing that?
Just look at the balanced equation and see how many you would need.
Okay, so 1.00 moles of oxygen is what you're given, right? Yes. So you need to multiply this by the appropriate conversion factor to convert from moles of oxygen to moles of ammonia.
3 over 502.
I'm sorry, Peter?
It would be, wouldn't it be, the conversion factor would be 4NH3
4
over
moles
502.
of NH3 over?
5 moles of O2.
Exactly. All right, so get my calculator here. Oh, I can tell you what this is. This is going to be equal to 0.800 moles of ammonia. All right? Okay, very good. What's the next step? Now that we have the moles of ammonia, what's the next step?
Can't we just plug it into the combined gas law?
Exactly. So the combined gas, not the combined gas law, I'm sorry. The ideal gas law. PV is equal to nRT, right? So we have to rearrange this to get an equation for V, which would be equal to nRT over P. Now the N we just calculated, that's a 0.800 moles of ammonia multiplied by R, which is always 0.0821 liters atmospheres over mole Kelvin times the temperature, which you have to convert to Kelvin. So that would be 850 plus 273. And I got 1,123 Kelvin. And then we divide all of that by the pressure, which is given as 5.00 atmospheres. All right, and that's it. The atmospheres will cancel out. Excuse me. The Kelvin will cancel out. And the moles will cancel out. So your final answer is going to be in liters. So 0.800 times 0.0821 times 11123 divided by 5. I don't know what's going on in my throat. According to my answer here, rounded off to 3 sig figs, that would be 14.8 liters. And that's how that is done. All right? Any questions about this? Any questions? Okay, so let me, is it okay for me to clear this? Okay, so let me clear this and scroll down. So the next question is, based on the same equation, how many moles of water can be prepared using 450 liters of ammonia at a pressure of 5 atmospheres and a temperature of 295 Kelvin? Okay, so let me hear your ideas as to how you tackle this problem.
Since we have the volume, the pressure, and the temperature, and gas constant, we can convert it to, we can find the amount of moles of ammonia,
Okay, so
and then
moles of ammonia is going to be equal to N, which will be which will be equal to PV over RT. All right. So P is 5.00 atmospheres. V is 450 liters. And then we divide that by 0.0821 liters atmospheres over mole Kelvin, multiplied by the temperature, which is 295 Kelvin. Okay, so let's see what this gives. So this is 5 times 450 divided by 0.0821 times 295. Okay, so according to my calculation, how many sig figs? 2 sig figs. So 93 moles would be the answer. All right, so atmospheres canceled out, liters canceled out, Kelvin cancel out. So you have 1 over mole, so that gives you moles as the final unit. So now we have the moles of ammonia. So the next step is what?
use the conversion factor to convert that many moles of ammonia to.
So 93 moles of ammonia. So what's the conversion factor? I need to scroll back to the equation above. Okay, so we're looking at the mole ratio between ammonia and water, right? So according to the equation right here, for every 6 moles of water, there's 4 moles of ammonia, right? So the way we would represent that down here is we're going to put 4 moles of ammonia below and 6 moles of H2O above. All right? So this goes with that, and that will give you the final answer, which is 93 times 6 divided by 4. So rounded off to 2 sig figs, that would be 140 moles of H2O. And that's how that is done. All right? Any questions about this one? Any questions? Any questions? Any questions? Okay, so let's move on to, I'm sorry, let me clear this first. And scroll down. Okay, so we did that. Okay, so now we're going to get into the Graham's law of diffusion questions, right? So if you remember, the Graham's law of diffusion, I'm sorry, effusion. I don't know if I told you guys, but, and I just did so. In a lot of textbooks, they confuse diffusion with effusion. These are two different things, right? So remember now, Graham's law applies to effusion. So I'm just telling you that because I think in one or two of these questions, they talk about diffusion when it should be effusion when it comes to the use of Graham's law. In any case, Graham's law of effusion says the rate of effusion of a gas is directly proportional to 1 over the square root of the molar mass of the gas. All right? So basically what this is saying is that everything, oh, by the way, there are two constraints here. One is that the temperature and the other is that the pressure is constant. So if the temperature and pressure is constant, then this would be the relationship between the rate of effusion of a gas and the molar mass of a gas, right? And there are different ways of measuring the rate of effusion, as you're going to see here. But one key thing you need to remember is that because of that relationship, you can conclude that the heavier the gas, the slower will be the rate of effusion, provided again that the temperature and pressure is constant, right? I remember giving a question in some tests back in it, before. And I don't remember exactly how the test is worded, but it would be something like this. Compare the rate of effusion of oxygen with hydrogen, right? Which would you expect to effuse at a faster rate, all right? You don't have to do any fancy calculations, excepting to determine the molar mass of each of them, right? So the molar mass of oxygen is about 32 grams per mole. The molar mass of hydrogen is about 2 grams per mole, right? So we can easily see that hydrogen would be the one that would effuse faster because it's a lighter molecule, right? So I'm just saying that, to help you so that if you're given a question like this, you don't have to go into any fancy calculation to find out which one effuse faster or which one effuse more slowly. Also, I want to say that the rate of effusion is basically proportional to the root mean squared speed of the gas, all right? So basically, you can use this as one way of measuring the rate of effusion of a gas. Okay, so with that said, let's look at question number 13. It says, in an experiment, it takes an unknown gas 1.5 times longer to diffuse than the same amount of oxygen gas, right? Find the molar mass of the unknown gas, all right? Now, based on this relationship here, we can relate the rate of effusion of the unknown gas to the rate of effusion of oxygen by this equation. Rate of effusion of unknown gas divided by the rate of effusion of oxygen would be equal to the square root of the molar mass of oxygen divided by the molar mass of the unknown gas, all right? Now, here's the thing. We were not given the rate of effusion, right? What we were given is the fact that the unknown gas diffuses 1.5 times longer, right? So it's talking about time, right? And if you understand the relationship between the rate of change of anything and time, you'll understand that it's an inverse relationship, right? In other words, the slower the rate of anything, then the longer it's going to take in terms of time, and vice versa, right? So we can add another piece to this particular expression right here, where we say that there's an inverse relationship between rate and time, so we can put time of effusion of oxygen divided by time of effusion of the unknown gas would be equal to all of these here, all right? So, so basically, all we have to do is focus on this part of the expression right here, right? Because we were not given the rate values or the relative rates, we were given the relative times, right? Now, according to this, it says that the time of effusion of, oh, before I do that, the question is asking for the molar mass of the gas. So we need to find mg. We need to find an expression for mg. So the first thing we need to do is get rid of the square root sign. So how do we get rid of the square root sign? We square both sides, right? So when you square both sides, you're going to get MO2 divided by mg is equal to the time of effusion of oxygen divided by the time of effusion of the gas. And because we're trying to find mg, then we can rearrange this to get mg is equal to time of effusion of the gas divided by time of the fusion of oxygen. Oh, I forgot to square this. Yeah, thank you. So this should be squared as well, multiplied by molar mass of oxygen, all right? And then we put the numbers in. Now, the thing is that they gave us this information here, right? The time of effusion of the gas is 1.5 times that of the effusion of oxygen. So therefore, we can say that Tg is equal to 1.5 TO2, right? Which means that Tg over TO2 is equal to 1.5. So basically, we can put 1.5 where we have that expression here. And of course, we know the molar mass of oxygen. So we just plug the numbers in, 1.5 squared multiplied by the molar mass of oxygen, which is 32.00 grams per mole. So that gives us 1.5 squared multiplied by 32. And according to my calculation, rounded off to 2 sig figs, the answer is 72 grams per mole. And that's how that is done. All right? Any questions about this? Yes, ma'am.
You did it so that it wasn't MO2 divided by mg, so it's just,
I'm sorry, where are we at? You mean here?
yeah,
Well, this here comes from this here.
yes,
So what we did was square both sides to get this expression here. So we still have MO2 over mg here.
yes,
We're trying to find mg.
yes,
So so basically what we did, I did something like cross multiplication where mg is switched with TO2 over Tg down here. You still have MO2 here, so MO2 would be equal to, when you flip it, you're going to end up with Tg over TO2 squared.
okay,
All right? And then you just put the numbers in. So it's kind of like cross multiplication in order, remember the aim is to get mg. You
Yeah.
want to isolate mg by itself.
yeah, so you
So
cross,
I brought this fraction underneath, this mg up here, right? So you're going to end up with MO2 over TO2 over Tg squared.
okay,
And then this would be equal to this here. So I basically skip this step right here,
okay,
right? And then I put the numbers in,
okay.
all right? Okay, any other questions about this? Any other questions, including you guys out there in Zoom? Feel free to chip in with your suggestions, or if you have any questions, feel free to ask. If there are no questions about this one, then let's clear this and move on to question number 14. Now, in this case, the question says, suppose a gas diffuses 1.4 times as fast as sulfur dioxide at the same temperature and pressure. What is the molar mass of the unknown gas? So again, you're asked for the molar mass of an unknown gas, but this time the question is asking, well, the question has given you the rates or the relative rates, because the question, and again, let me just say this. When it comes to these types of questions, it's very important that you interpret the question carefully, right? In the previous question, it tells you that the unknown gas diffuses 1.5 times longer than oxygen. So that's basically a time-to-time correlation or relationship, right? In the case of this question, it says that the gas diffuses 1.4 times as fast as sulfur dioxide. So what that is telling you is that the rate of diffusion of the gas, I'm just going to express it over here, the rate of diffusion of the gas will be equal to 1.4 times the rate of diffusion of, what's the other gas? Sulfur dioxide, right? That's what this is telling you. This is telling you the relationship between the rate of effusion of the unknown gas and the rate of effusion of sulfur dioxide. So the question is asking, what is the molar mass of the unknown gas? Okay, so basically, we can say that the rate of effusion of the unknown gas times, or not times, divided by rate of effusion of SO2 would be equal to the square root of the molar mass of SO2 divided by the molar mass of the unknown gas, right? And the question is asking for the molar mass of the unknown gas. So just like we did before, because you have the square root sign here, we have to square both sides to get rid of it. So you're going to get rate of effusion of gas divided by rate of effusion of SO2 squared. would be equal to the molar mass of the SO2 divided by the molar mass of the unknown gas, which means that the molar mass of the unknown gas would be equal to the molar mass of SO2 times rate of effusion of SO2 divided by the rate of effusion of the unknown gas squared. And then we put the numbers in. So we need to calculate the molar mass of sulfur dioxide, which is, if I remember correctly, sulfur is 32.07 plus 2 oxygen, which is 32. So according to my calculation, the molar mass of sulfur dioxide is 64.07 grams per mole. And then this ratio here is the same thing as 1.4. So I'm just going to multiply by 1.4 squared. 1.4 squared because, actually, wait a minute. Hold on, wait a minute. This should be, I'm sorry, this should be 1 over 1.4 squared. Because based on what I have here, rate of effusion of the gas divided by rate of effusion of SO2 would be equal to 1.4, which means that this ratio here is the inverse of that. So this should be multiplied by 1 over 1.4 squared. And let's see what that gives. 64.07 divided by 1.4 squared. So according to my calculation, this works out to be equal to, rounded out to 2 sig figs, 33, and the answer, I mean, the units would be grams per mole. All right, that's how that is done. Any questions? Any questions? Okay, let's clear this. Okay, so the next question is asking for you to calculate the relative diffusion of the relative rates of diffusion of chlorine to krypton, right? So basically what the question is asking for you to do is to determine this expression here, what this is equal to, rate of effusion of chlorine divided by rate of effusion of krypton. So that would be equal to the square root of the molar mass of krypton divided by the molar mass of chlorine. So we go to the periodic table. Let's see here. Let me go to the tables here. Or you know what? Let me just look up the molar mass of krypton. (83.80). So that will go here. 83.80 grams per mole, and then divide that by the molar mass of chlorine. Now that one I know because chlorine, one chlorine atom is 35.45 times 2. So that would be down here 70.90 grams per mole. All right. Okay, so all we have to do now is crunch these numbers. 83.30 divided by 70.90, and then find the square root of that. And according to my calculation, the answer when rounded off to 4 sig figs is going to be equal to is going to be equal to 1.084. So basically what that means is that chlorine will effuse 1.084 times faster than krypton. And that's it. And that's how you do that part. All right? Any questions about this one? Any questions? Any questions?
You just leave it as 1.084. You don't have to change it in a percentage.
No, no. I mean, you can if you want to, but you don't have to. Yeah, just leave it like that, I would suggest, right? Because the question is asking for the relative rates. Basically, how much faster is one compared to the other. Okay, any other questions about this? Any other questions? I think, oh, okay. So let me clear this and move on to question number 16. Now, in the case of question number 16, they gave you the speed of presumably a nitrogen molecule, right? So this is one way of measuring the rate of effusion because the rate is basically correlated to the speed of the molecules, right? So this is the velocity of nitrogen, and it's asking for the rate at which hydrogen sulfide will travel under the same experimental conditions. So in this case here, we're comparing nitrogen to hydrogen sulfide. So I would say that the rate of effusion of H2S divided by the rate of effusion of nitrogen will be equal to the square root of the molar mass of nitrogen divided by the molar mass of H2S, all right? And since the question is asking for this, I'll just rearrange this to get the rate of effusion of H2S is equal to the rate of effusion of nitrogen multiplied by the square root of the molar mass of nitrogen divided by the molar mass of H2S. And then I'll plug the numbers in. Now, one number that we have already is the 35 centimeters per second, right? So the molar mass of nitrogen would be 14.01 times 2, so that would be 28.02 grams per mole. And then in the case of hydrogen sulfide, that's 32.07 plus 2 times 1.008. So according to my calculation, this works out to be equal to 34.09 grams per mole. And then we do the calculation. So 28.02 divided by 34.09, and then we find the square root, and then we multiply by 35. And according to my calculation, this works out to be equal to 32 centimeters per second. That will go, all right? And that's how we do that. Okay, any questions about this? Any questions? Okay, let me clear this. Okay, I think this is the last question. Oh, two more, okay. Okay, so let me hear what you have to say about this one, based on what we have covered so far. In this case, the question says, it took 56.3 seconds for a given volume of chlorine gas to effuse through a pinhole under the conditions of temperature, under the given conditions of temperature and pressure. How long would it take for the same volume of diborane, and it gives you the formula, to effuse through the same hole under the same conditions? All right, so let me hear what you have to say about this. How would you tackle this problem? It's the same idea from the previous problems that we're going to use in this case. But please note that the question gives you what? Time, not rate, right? Okay, so that's kind of important for you to recognize.
Do we need to convert the time into the rate?
No. In fact, no. Let me remind you of what I said earlier. Remember I said that the rate of effusion, this is Graham's law, is proportional to 1 over the square root of the molar mass of that gas. The rate of effusion of the gas is proportional to 1 over the square root of the molar mass of the gas. And that would be proportional to 1 over the time of effusion of the gas. all right? Because of the inverse relationship between rate and time. The longer something takes, the slower will be the rate. The shorter time it takes, the faster will be the rate.
So we can just,
Okay, let me hear what you have to say.
we can figure out the molar mass of both of them.
Okay, yeah,
So-
okay, let's do that first. So for chlorine, I think I did that earlier. The molar mass of chlorine is 70.90. 70.90 grams per mole. And the molar mass of diborane, no, that I'm too lazy to calculate, so I'm just gonna
And to be clear, we are doing, it's gonna be square root of MCl over square root of MB2H.
it doesn't matter the order in terms of what.
We have the T set up the same way.
Exactly, exactly. Okay, so what was I looking? Oh, diborane, B2H6. So calculate, okay, I got 27.67 for the molar mass of diborane. I'm going to write that down here. 27.67 grams per mole. All right, so got that out of the way. So what's the next step? Now that we have the molar masses of both the chlorine and the diborane, what would be the mathematical relationship between the time of effusion for each gas and the molar masses?
Square root of the molar mass of chlorine over the square root of the molar mass of diborane equal to the time of diffusion of chlorine over the time of diffusion of diborane.
Very good. That would be the equation which relates the time of effusion of each gas to their respective molar masses. Oh, this should be, I'm sorry, hold on, let me correct this here. This should be MB2H6. All right? Okay, now the question is asking for what? The time of effusion of diborane. So basically we have to rearrange this to get TB2H6, and that would be equal to TCl2 multiplied by the square root of B2H6, I'm sorry, the molar mass of B2H6, the molar mass of B2H6 divided by the molar mass of the chlorine. And from here, it's all a matter of plugging the numbers in. So for chlorine, the time of effusion was 56.3 seconds multiplied by the square root of B2H6, which we determined to be 27.67 grams per mole, all divided by the molar mass of chlorine, which is 70.90 grams per mole. And that's it. So let's see what this gives. 27.67 divided by 70.90, and then find the square root of that, and then multiply by 56.3. And my calculation tells me that the answer should be, okay, rounded off to 2 sig figs, 35.2 seconds. And that's it. All right. Any questions about this?
I do have a question.
Yes, ma'am.
In all the previous problems we did when we were using that equation, the elements were on alternating sides. If that makes sense, like one would be on the denominator and the same element would be on the numerator.
Okay, so
Why is it?
in this case here, when it comes to the time of effusion, yes, these terms would be correspondingly in their relative positions as shown, right? But if you're talking about rates, that's different. It would be inverse. In other words, the rate of effusion of B2H6 would be up top here, divided by the rate of effusion of Cl2.
Okay.
Right? This here is Graham's law, right here, as applied to this system, right?
Okay.
The rate, according to Graham's law, the rate of effusion is directly proportional to 1 over the square root of the molar mass, right? But that's rate. We're not talking about time.
Okay.
But because there's an inverse relationship between rate and time, that's how we end up with this part right here.
Okay.
You see what I'm saying?
Yeah.
So that's why I'm stressing that when it comes to answering questions, read the question carefully,
Okay,
right? When it comes to Graham's law of diffusion question. If the question is worded in a way to talk about rates, then this is the expression that you'd use.
okay,
But if the question is worded in a way in reference to time of effusion, this is the relationship you'd use.
okay,
You see what I'm saying?
yes.
So that's basically how that works out.
So
All right.
diffusion deals with the rate of diffusion.
I'm sorry?
Diffusion would deal with the RG, and then effusion is gonna deal with the
No,
time.
the diffusion. Okay, so here's the thing.
Diffusion follow the same law
No.
generally?
And the reason why is because of the definition of diffusion and effusion. Diffusion is basically talking about how a substance spread into another substance, right? So let's say you have a container filled with, let's say, one gas, carbon dioxide, and then you add to it hydrogen, right? Basically, diffusion is talking about how the hydrogen will spread through carbon dioxide. Now, effusion is where you have a gas escaping a container through a small hole into vacuum. That's the difference. So there's a big difference between effusion and diffusion. But unfortunately, including what we have here in this assignment, and in a lot of textbooks, there's a confusion between the two. People tend to, in some cases, talk about effusion and diffusion as if they mean the same thing. They don't mean the same thing. And the reason why, well, we use Graham's law with respect to effusion, and that's because Graham's law works best in terms of predicting certain aspects of fusion, because when a molecule or when gas molecules escape into a vacuum, they don't encounter anything else. So there's nothing else to disturb its movement because it's in a vacuum.
They're going into a vacuum of where there's no matter at all.
Exactly. So therefore, Graham's law works best in terms of dealing with that. Effusion, it won't work because when a gas is escaping into another gas, it's going to bump into other gas molecules, and therefore the law will not work well because of that reason. All right. So that's why it's important that you understand the difference between effusion and diffusion.
So
Mhm.
the formula we would use for effusion though is still
It's still
similar. It
Right.
deals with time.
right. Exactly. So yes, it deals with time. This here is the actual effusion law, Graham's law of effusion.
Right.
But of course, you can relate that to time because of the inverse relationship between time and rate. All right, so that's that. All right. Man, you guys are giving me some ideas for questions for your next test. Anyway, let me clear this here. And I think we have one more question. Number 80. Okay, let's hear what you have to say about this one. In this case, they gave you the time of effusion of CH4, which is known as methane. Hold on 1 minute. Okay, so they gave you the time of effusion for methane, and they said it's STP conditions. And then it says, how long will it take for the same volume of this gas to effuse through the same hole under the same conditions? Okay, so let's hear what you have to say about this one.
So standard temperature and pressure, which doesn't really matter.
So it's gonna be the square root of the molar masses is equal to the time.
I'm sorry. Okay, what are the guesses? CH4
Yeah, CH4
and
and then
NF.
NF3,
right? And that's equal to what now?
T of CH4
Mhm.
over T of NF3.
Good, okay.
Um,
And what the question is asking for?
The question, we're looking for the volume of
Oh,
NF3. Or the time of NF3.
exactly. So this is what you're trying to find. So TNF3, NF3 is equal to TCH4 multiplied by the square root of N of M NF3 divided by M CH4. And that's it. So TNF3 is equal to, okay, so TCH4 is 97.0 seconds multiplied by the square root of the molar mass of ammonia. Okay, so I have to, okay, so, not ammonia, NF3, what am I saying? Ugh. Let me clear or erase. Anyway, this should be NF3. All right. So going back to here now. NF3. Calculate. And what does that give? That gives 71.00. So that would go here, grams per mole. And then for methane, I can calculate that 12.01 plus 4 times 1.008, 16.04 grams per mole. Okay, so let me go back to this. Okay, so this is what we need to work out. So let me divide 71, divide by 16.04, and then find the square root of that, and then multiply by 97. Whoops, 97. Okay, so I got, and please correct me if I'm wrong, but I got how many sig figs? 204, 3 sig figs. 204 seconds as the time of effusion of NF3. Okay, so that's basically how that is done. Any questions about this? Any questions?
How do you determine which element is in the denominator and which in
It
the,
doesn't matter really,
okay,
as long as,
The rate is going to be the same as long as they're both on the same.
right, if you're looking at the time molar mass relationship, they're on the same, what's the word I'm looking for? Like,
Same on the top, same on the bottom.
exactly, right. Now, in terms of rate, it's the inverse. You see what I'm saying? But it doesn't matter the order.
no matter where you put which one,
Right, as long as it parallels.
Yeah.
Right, on the other side. Okay, so that's pretty much it for this. So of course, your upcoming test, and again, that test will be on not Wednesday coming, but the Wednesday after. What am I saying? Yeah, the Wednesday after, because I won't be here on Friday. And that test will cover chapters 3, 4, and 5. All right. I've already sent you guys have received or should have received your graded assignment 3. I'm going to send you your graded assignment 4 this evening. And as far as this assignment is concerned, let me see here. I need to get this soon because I want to get it back to you so that you guys can use that to help you to review. Let me clear this. Okay, so assignments. Okay, so this is assignment 5 I'm setting up now. Okay, so today's the 10th. Okay, is Sunday a reasonable time for you to submit it?
Sure.
And the only reason why I'm, choosing such a date is because, I want to get it back to you guys ASAP. Okay, so available from today to Sunday at midnight. Okay, so that's it. All right. So make sure you submit it by then. Make sure it's in a PDF format. And of course, you know what? I'm going to post an announcement because some students, and I'm not saying this is true for you guys or all of you guys, but some students have been not obeying the guidelines I've set out for submission of these assignments. So I'm going to do that maybe later on this evening if I have the time. Okay, that's pretty much all I have planned for you guys today. And you guys are now caught up with the other group I'm teaching. So I'm not too keen on starting a new topic today. So the next topic we're gonna talk about is thermochemistry. So I'm going to start that topic on Wednesday. All right. So if you want to read ahead, that's chapter 6. If you want to read ahead about that, I have no problem with that. All right. I think I can't think of anything else, unless you guys have any questions you want to ask, but I can't think of anything else if I remember anything else, I'll just post it in the announcement. All right. So that's pretty much it for today, folks. So I'll see you guys next Wednesday. Oh, somebody has a question out there in Zoom. Can you have a cheat sheet for the test with all the gas formulas? Well, some of the formulas are already in the handout that you're going to get, the tables. So, but not all of them. So, but you should be able to derive those other equations. So, short answer is no. But some of the equations, like the ideal gas equation, will be, I know that equation is in the packet. All right. So I hope that answers your question, Miss Anwar. Okay, if that's all the questions out there in Zoom, I'm going to sign off now.